Greetings folks, and welcome to the latest edition of the Physics Corner. This is a video series in which we set up and solve introductory physics problems at the college level. I'm your host, Dr. Christopher Cirola. Fair warning, today is going to be a little bit of a longer video because we have a pretty intricate problem to tackle, but it is also well within your means, assuming you have your algebra skills at hand. So, let's begin. Let's suppose we have a mixed resistor circuit. Now, this is not an official term, so what do I mean? I mean that it's neither a series nor a parallel nor even a true mixture of series/parallel resistor circuits, but rather we have two, not one, sources of voltage, and we have a multiplicity of resistors, and therefore we can't approach it by either solving for straight up series or resistors and get effective resistance. We have to take a different approach. So what I'm also going to show you is a physics version of how to do this. Now, electrical folks, the people that teach, say, electrical circuits for a living, electrical engineers and that, they have some shortcuts. But we're emphasizing this particular approach in this problem-solving session because this makes use specifically of physics principles. So while you might find shortcuts if you, say, become an electrical engineer or a technician, we're showing the physics version of it for that reason. So let's get started. Let's imagine we have a circuit that looks something like the following. There's 12-volt battery here and a 10-volt battery here. In between, we have a junction here, and there's also a junction over here, and we have a variety of resistors. Now, each battery, by the way, also has internal resistance of 1 ohm, so I've labeled those here and here. This, by the way, is a typical physics version of drawing this out. We put a resistor symbol next to the battery or source of potential difference. Even though this resistor belongs to this, it would actually be inside of it. That ends up making for a pretty messy picture, and so we don't do it that way. But that's what this represents. So this 1 ohm and this 1 ohm both are the internal resistances of these two batteries. All right. Then, on top of that, we have a resistor of 11 ohms, resistor of 8 ohms, and a resistor of 15 ohms in the locations currently cited. So we have a total, if you will, of 5 resistors and 2 batteries. What can we do to solve this problem? First things first, let's simplify. Now, I mentioned before that we aren't, say, combining or using series and parallel resistor formulas, but a little bit of a misleading flag there, I'll say at the first glance here, because if you look, this 11 ohm resistor and this 1 ohm resistor are sort of along the same line. Now, yes, this wire is drawn as though it kinks right here. That is for the purposes of drawing this circuit diagram more than the actual wires in a real circuit. Remember, a circuit diagram is not a blueprint. It's not a scale picture of how the wires are actually situated. Rather, it's better read as a set of directions showing you how to hook things up. And also remember that this resistor here really is part of this battery. So that means that this resistor and this battery, if you look, are along the same wire that starts at this junction, goes along here, and ends at that junction. And because of that, these two resistors are essentially in series. Similarly, now that I've described it, if you look carefully, this internal resistance and this resistor are also therefore in series. And so, for simplification purposes, we can re-sketch the picture. So we now have our 12-volt battery here, our 10-volt battery here. I can remove the internal resistance for the purposes of the solution of the picture, if you will, and just simply sketch in the 3 resistances like this. Now, this 8 ohm resistor in the middle is not changed, but 11 plus 1 is 12, of course, and 1 plus 15 is 16. And so for the purposes of solving the problem, I can recast the picture like this. Why then go to all the trouble of drawing it with the internal resistances? Well, first off, that might be something you don't actually know at the beginning of a problem. An internal resistance, if you do some of this work in detail, depends not just on the battery itself, but actually how much current is flowing through it. So we're already making an approximation. And second, we do need to see that this is an actual thing. Remember that actual real devices like real batteries or real power supplies do have internal resistance, and so we would need to account for that in practical problems. So, with that in mind, what's the next step? Well, this is a little tricky, but it's also something that we can do. I mentioned this before. If you look at this picture here, we have 2 junctions, here and here. Now, again, these kinks at these corners here are not real kinks. This is just for purposes of sketching a picture. Rather, this is just to make it easier for us to see what's going on. But in a real circuit, there wouldn't necessarily be a kink here, and it's certainly not a junction. The current that's flowing here will simply keep on going this way. It's not going to change value just by encountering this corner, for example. And so the current that starts, say, at this junction here and flows in this path until it gets to this junction here, that'll be the same current. Remember how this works. In the DC circuit especially, current will be the same throughout an entire section of wire. And so what we can do is we can describe or sketch arrows to describe a current flowing in this section. I'm going to label that current I sub A, just to give it a label. And I could call it I1 or I whatever, but I'm going to call it I sub A for our purposes today. All right. Similarly, we have a second idea. We can talk about starting at this junction and current flowing through this battery, and of course its internal resistance, through the rest of the circuit like this until it reaches this junction. And I'm going to call that I sub C. You'll see why I'll do that in a moment. And then there's a third possible way to, or place to have current. That's from the junction from here to here. That's simply going down like this. And I call that IB like that. All right. So next thing is, well, why am I drawing arrows? I mean, is current really a vector quantity as such? Not in the strictest sense, right? A vector has a magnitude and direction. And the direction, if it's a true vector, is not changing. And as you'll notice, this arrow here changes direction here and goes up like that. Now, I did say that this doesn't look like a true circuit that you put together, but you still have the same issue, right? You'll still have a junction here, and this wire will curl around, or wires will curl around until it meets this junction here. So the current will officially be changing direction. So it's not truly a vector in the strictest sense of the word. But there is still a directionality going on, right? So that's one thing. And it matters because the current could be flowing in this general sense, or possibly be flowing from this side and going like that. So why make this choice? Well, I'm going to kind of guess ahead a little bit. Without solving the problem ahead of time, we can make this guess. If you look at this symbol here for the battery, batteries are gauged or drawn so that this is the positive end, the long side, and the short side is the negative end. And current flow is going to be pushed, if you will, in that direction. So because it's 12 volts, it's the biggest source of voltage in the entire circuit, I'm going to make the guess ahead of time that current will tend to flow in this direction. Now, let's suppose that I've guessed incorrectly. Let's suppose that that turns out that instead of going, say, in this sort of clockwise direction I've got sketched here, let's suppose it actually is going counterclockwise. And maybe that happens. Well, what will happen is that if we do our solutions properly and I solve for the amount of current flowing, that won't change the amount, it will change its sign. So suppose I solve and I find a current, and by the way, this won't be the answer. Suppose I found a current of 1 amp. If it's a positive 1 amp, then that positive means that I've thrown in the correct direction. If it turns out to be a negative sign, say a negative 1 amp, then the arrow really should be pointing this way and the current be flowing in that direction instead. So we don't have to worry about the amount. We do have to take a direction, though, as you'll see when I set up some equations to work this problem. Okay. Similarly, because the 12 volts is bigger than the 10 volts, I'm going to guess, reasonable guess, that the current through the middle section will go in this direction, because you can see it's going to push it like this. This battery will try to push it backwards this way, but let's find that out. And the 10 volt and 12 volt battery both together are quote unquote pushing the current in this direction, so I'm going to choose IC to go in this direction here. So again, these are guesses, and like I said, I could turn out to be incorrect about that, but it won't matter if I do my math very carefully. If I do my math correctly, watch my algebra steps, I will get the correct magnitudes of the currents, even though the signs will be different. And all the sign difference means is that my arrows need to be pointing the other direction. So that's something to be determined. All right. So how then do we get started on a solution for a complicated circuit like this? Well, I already mentioned we can't really use, say, the additions of resistors in series, not anymore really, or resistors in parallel. It doesn't really work that way very well, at least not in the physics sense of the way we are talking about. Rather, let's go to some old standbys. And you might remember that we actually used these ideas, these concepts, to find those rules for series and parallel circuits in the first place. And that is conservation of current and conservation of voltage, right, or energy. So what does that mean? First off, the sum of current going into a junction is equal to the sum of the currents coming out of a junction. Now, what is a junction? Let's refresh our memories on this. I've been saying it. Let's refresh our memories. A junction is a point here where the wires all join together. We have 3 wires coming together like this. By the way, if you only had 2 wires, if you could get rid of this one here, there really isn't a junction, right? So you have to have a minimum of 3. Now, it is possible, of course, to click the 4th or 5th or however many wires you want to this one spot. That would just simply make our problem more complicated, but it won't really inform us anymore about the physics. So we're going to go with the simplest possible junction, and that is 3 possible wires or regions where the current can have different values. All right. Now, one other thing about it, I have a junction here, and therefore, of course, a junction here. If you have a circuit like this, you must, if you have one junction, have a second junction because, as we all know, complete circuits have to come in loops, don't they? Otherwise, you won't have any current flowing. Therefore, if you split off in one place, you must bring those wires back together in another location. So that's one of the rules, is conservation of current, or conservation of charge really is where that comes from. We haven't really encountered conservation of charge too much, at least not explicitly in problems before, but that is a fundamental law of nature, right? Similar to conservation of energy or conservation of momentum. It's the same kind of idea. It's one of those fundamental laws. So let's apply that. That says the sum of the currents going into a junction equals the sum of currents leaving a junction, all right? So let's take a look at this junction here. So if we look carefully, current A is coming into the junction, current B is leaving the junction, and current C is also leaving the junction. So I could make this an equation. IA, there's no sum because there's just one of them, is coming in, and that's equal to IB plus IC. Now I'm going to label that equation for convenience right there. We'll come back to using that later on for purposes of solving the problems. Now, what about the second junction? So if you look carefully, IB comes into this, IC comes into this, so IB plus IC, IA is leaving it. That would be IB plus IC equals IA, which is to say, if you have 2 junctions, you only get one useful equation. You get the same equation. So there's only one current equation to write for a circuit like this. Now, if I had more than 2 junctions, I would have more equations, right? As a matter of fact, the number of equations I'll have will always be at least 1 less than the number of junctions. But again, we don't need to go any further than this. This is sufficient for purposes for us here. So that's the first equation. Turns out it's vital to have that equation. I'll show you why in a little bit. All right, what's the other major rule? Well, I had conservation of charge, or current flow. Now let's talk about conservation of voltage, or to get more fundamental, conservation of energy. Conservation of energy in a current or a circuit like this can be expressed in this fashion. The sum of all the voltages in a complete loop must come up to be 0. Let's think about that. Why would that be the case? Because the amount of voltage or energy supplied by a power source like a battery has to be equal to the amount of power or energy used, or voltage used, by all the various devices like resistors and such in a circuit. And that has to sum up to be 0, otherwise energy is not conserved. You're either losing energy or gaining energy from nowhere. So it has to be like this, right? So if we look at this carefully, there are 3 possible loops. Let's take a look at, say, what I'll call the left-hand loop first. And I'll go in order just to show off what I'm talking about. So what do I mean by the left-hand loop? If you look carefully, I have a loop that's the left-hand side of this picture, isn't it? So let's start with the battery, and it's 12 volts. Now, I've got everything expressed in terms of standard units, right? Volts and ohms. And of course, when we calculate our currents, there'll be amps. If I'm careful with that, as long as I don't use any prefixes or mess with the numbers, my units will end up being what they need to be. So just for convenience sake, I'm going to leave off the units as I'm writing my equations. So, but with that in mind, 12 volts. So I pick up 12 volts. That's the language you use. I go in this left-hand loop. That means I go down this way. I hit this resistor. There's 8 ohms multiplied by the current, unknown current IB. Now, what is that all about? Well, we all know from Ohm's law, V equals IR, right? In fact, let me write that off to the side so you can see what I'm talking about. Now, this isn't just a equation that is useful for, say, an entire circuit. It's used for individual parts of a circuit, which means the voltage that I am using, or the voltage I quote-unquote drop at a particular device, is equal to the current multiplied by the resistance. So I have 8IB, like that. Now, one more thing to draw in here. I'm going in the same direction as the current as I'm making my little circle as I'm drawing this. And the whole point of resistors is that's going to use energy or use up voltage, right? So if I use it, I subtract it. So I have a negative 8IB like that. All right, continue onwards. Go like this, come up here. By the way, unsaid, we're assuming all the wires are of negligible resistance, or we could have incorporated those into the internal resistance, if you will, and so on and so forth. We're assuming for simplicity that the wires themselves don't have any resistance worth worrying about. All right, so anyway, come back up here. I get to this resistor here. It's 12 ohms worth. I'm still going in the same direction as my current flow, and IA is the variable, so subtract 12IA, like that. And then I come up and I'm back to my original battery again, so I've completed my loop. And I set that equal to 0. So again, let's go through that real quick one more time. I start here, go in a loop like this, complete the loop. The sum of the voltages must be 0. Okay. One more thing, given the numbers I've got here, I might as well do a little bit of simplification quick. If you notice, each of these is divisible evenly by 4. So 12 divided by 4 is 3, so I get a 3. 8 divided by 4 is 2, so 2IB minus a 3IA. And of course, 0 is unaffected. And I get an equation like this. And I'll label that equation 2 for simplicity's sake, so we can keep track of it. All right, so that's my left-hand loop, and it gives me another equation. Okay. How many equations do I need? Sounds like I need to keep on going, but why? And how many am I going to have to actually use? Well, ultimately, we need 3 independent equations, don't we? We have 3 unknown variables: current A, current B, and current C. Therefore, we need at least 3 independent equations to solve for that. I've got 2 so far, equation 1 and equation 2. Need at least 1 more. Well, how can we get that one? Well, let me tackle the right side then, the right loop, if you will. And let's take a look at an equation we can form for that one. So I'll start here and then go in this right loop, which means this path like this, okay? So 10 volts, I pick up or gain 10 volts, if you will. So again, we're leaving off the units for convenience sake. Come down here, I'm in the same direction as the current arrows that I've drawn. So I subtract 16IC, like that. Keep on coming around here. Now this is where it gets interesting. Notice as I'm making my loop, I'm now going in the opposite direction of the arrow for IB. What's the same as subtracting a negative? Adding. So instead of subtracting 8, I add 8IB. And then complete my loop. And I get 0 like that. That's important. This is where the signs matter, and this is why we had to define directions for our current before we got started. There's a temptation to just subtract all these like this, because after all, that's what a resistor's job is, right? It's to use up voltage. But what if you're subtracting a negative? What if you're using up the opposite? You need to account for that mathematically, and this is how we do that. One more thing. These numbers can be reduced a little bit further for simplicity. Each of these is divisible by 2 in this case. So 10 divided by 2 is 5, of course. We have a negative 8IC here. We have a plus 4IB equals 0 like that. And I'll call that equation 3 for convenience. All right. One more thing, just to double check on this. I want to show this off to make sure that it's understood. What about the outermost loop? Because there is a third loop here, right? If you think about it, we could start here and go all the way around the outside and skip the middle entirely. Is that legit? Yes, it is. all you need is to complete a loop. You don't have to include every single part of the circuit, right? If you look carefully, we didn't for these other two loops, did we? So let's do the outer loop, right? So the outer loop, we'll start here. And again, this is just me picking a point of convenience. So here it's 12, right? Pick up 12. Then I'm going in the same direction as this battery, so it's plus a 10. I go over here, subtract 16 IC. Keep on going this way again. We're skipping the middle. You're going in the same direction as the current here, so minus 12 IA, and then complete my loop. Now, I want you to look very carefully, and I'll let you check on this yourself, but compare this equation I've just created here to this one plus this one. So 12 plus 10, negative 12 IA, negative 16 IC, and then check out what's happened. A negative 8 IB plus 8 IB, which cancels. In other words, combining the left loop and the right loop gets you this equation here. That's not helpful. It doesn't change anything. It doesn't add anything to our knowledge. So this is not, in other words, an independent equation. It's a dependent equation. And therefore, we don't have to use it. Now, it's a matter of convenience or a matter of algebraic work, if you will, as to which two of these three equations we want to choose. Now, I've already looked at this problem, as you might expect. I'm going to use these two. Okay, so that's why I worked on those first. But it is, at least in theory, possible we could make use of this equation instead and one of these others. So we do have to use two out of those three voltage equations. But we can't use all three of them because we'll be spinning our wheels. We'll be doing extra work and not getting anywhere if we do that. So you have to have three independent equations to make this go. And that's what we're going to be doing. So while I've written this equation, I'm not going to end up using it for that reason. Right, so that completes the setup stage of our problem, if you will. So the next step is to start solving the algebra. So, by the way, at this stage, we have pretty much done the physics work, if you will. All the physics contemplation, that the physics, if you will, is the application of this rule, the application of this rule. So I've created these equations using my physics. At this stage, it now becomes an algebra fight. So let's have that battle. Now, I will occasionally, by the way, bring back this picture to refer to this here if I need to, okay? So, where do we start? Well, we already know that if we combine equations 2 and 3, the two voltage equations, we just create a third voltage equation which doesn't give us any new knowledge. So doing that doesn't help, which means if we want to go anywhere, we need to use the current equation, at least in some sense. So let's do that. So I'm going to go ahead and take equation 2, which was, we'll copy back down, 3 minus 2IB minus 3 equals 0, like that. And let me write down the first equation, which was IA equals, oh, this should be a 3IC, sorry, IB plus IC, like that, okay? All right, so, and this was IA. Make sure I get this correct, right? That was IA. That's very important to have this correct. That was not IC, my fault. That was IA. You need to make sure I substitute correctly. So, I've already got this solved for IA, so I'm going to take this and substitute into that equation. So, in other words, my process is sub 1, equation 1, into equation 2. All right? So, that means I have 3 minus 2IB minus 3. Now, instead of IA, it's IB plus IC. And I'm taking the extra step of writing this out in parentheses so everybody can see exactly what I'm doing and where it's coming from. Okay? So, this is an algebra trick, right? Straight substitution. All right, the 3 and the 2IB, let's leave those alone for the moment. And let's distribute the negative 3 between these two terms. So, a negative 3IB and a negative 3IC equals sort of like that. And then these are IB terms. So let's combine them. Negative 2 and a negative 3 is a negative 5. So 3 minus 5IB minus 3IC equals 0. And for simplicity's sake, I'll call that equation 4. And again, you don't have to label your equations. That's just me doing this for our purposes of showing the solution here today, right? But it comes in very handy. So I'm going to do it that way. All right. Now, what do we do next? Okay. Well, we need to bring back in our third independent equation, right? And that equation, copy that down, was equation 3 originally, and that was 5 minus 8IC plus 4IB equals 0, like that. Okay. Let me write this equation right underneath it. So I have a 3, and let me rearrange a little bit. So 3 minus a 3IC and minus a 5IB equals 0 there. So I've just simply taken my equation I created from the first two equations, and I'm going to compare it to this third equation. Now, I've got it written like this on purpose for a reason. If you do this, you can sort of see what a thing you can do. Let's go ahead and see if we can eliminate one of these variables. We have two equations and two unknowns, right? We want to get rid of one of the variables, so we have one equation, one unknown, don't we? Okay. Well, let's go ahead and try that. Now, here's going to be my trick. If you look carefully, these two numbers are both negative signs on the IC, so let's leave those alone. But I have a positive sign on this IB and a negative sign on this IB. So if I can make these equal to each other, plus and a negative, I can cancel them out, can't I? What's a way to do that? Let's take this equation here and multiply by 5. Let's take this equation here and multiply by 4. Now, why 5 and 4? 5 times 4 gives me a positive 20. 4 times a negative 5 gives me a negative 20, doesn't it? And I'll be able to cancel those. So, always when you're doing these kinds of things, be very careful, follow your steps very carefully, on purpose, so that you can see exactly how it works. So, 5 times, now again, this has to be multiplied by the entire equation. This 4 has to be multiplied by this entire equation in order for this to make sense. So let's do that, all right? Okay, so 5 times 5 is 25. 5 times 8, negative 8, is a minus 40 IC. And 5 multiplied by 4 is a positive 20 IB. And of course, 5 times 0 is still 0. Okay, so we got that. How about this equation? 4 times 3 is 12. 4 multiplied by negative 3 is a negative 12, like that, IC. And 4 multiplied by negative 5 is a negative 20. That's the whole point of this little exercise. I get that. And now if you look carefully, I can add the two equations together, can't I? So 25 plus 12 is 37. 40 and 12, both negative, is a negative 52. IC. And then 20 and negative 20 cancel. And now I've got a very simple equation to solve, don't I? One equation, one unknown, all the numbers are there. So IC then is equal to, if I draw this over, I put IC on the other side. I have to divide by 52 to take it out. 3750 seconds, if you will, amps. I'll put the unit back in place so you can see what that is. And if you prefer to have decimals, which at some point you usually do, it'd be 0.71 amps. Now, I've been using two significant figures for my numbers so far, so let me do the same thing here, and that's what I get. All right. Now, I'm going to keep the fraction for use later. You'll see that comes in very handy. But for the moment, we could either represent this way or this way, right? So we'll do that. Okay. All right. What's our next step? Well, we've got one of the unknowns solved for. Let's find the others. Now, what's an equation to solve for one of these other unknowns? Let's go back up to this one. Okay, so let's see here. Or, excuse me, this, where are we looking at? This one right over here. 3 minus 5IB plus 3IC, minus 3IC, excuse me, equals 0. Let's take a look at this one here. Let's put that to work. All right, so let's rewrite it. So go back to equation 4, and I have 3 minus 5IB minus 3IC equals 0. All right, let's plug in the numbers and solve for IB. So first off, let's get IB by itself. So we have a 5IB. If I add it to both sides, will equal a 3 minus 3IC over here. Or if you prefer 3, then 1 minus IC like that. That actually might look a little bit easier to solve. Okay, IB by itself, divide both sides by 5, 3/5, 1 minus IC like this, equals a 3/5. Now it's 1 minus 37/50 seconds. And this is why I kept it like this for my purposes. You could use the decimal version of this, but decimals have a tough way of treating this if we don't have enough significant figures. So it's usually a great idea to keep a fraction around until you report your final answers. Okay, so that's what I'm doing here. All right, well, what is 1 minus 37 over 52? Well, there's 52 of these, right? So again, just to make sure it's very easily seen exactly what I'm doing with my math, so I'll convert 1 to 52 divided by 52, right? Do it that way. So 3/5. 52 minus 37 is 15, mind you, right? And 52 like that, okay? And again, there's another advantage of using fractions as long as you can get away with it, because sometimes you have some things simplify. So 15 and 5, I get a 3 like that, and ultimately it's 9 over 52. That's in amps again. And of course, we can convert that into a decimal form and get that number as well. Okay, I had to do a quick adjustment. We're back. So if we do this calculation, we get the 15 and 5 cancel each other. 3 times 3 is 9, 9/50 seconds, 0.17 amps. By the way, notice something that's happened. I managed to guess right, it turns out. Both of these numbers are positive currents, which means the arrows I drew are in the correct directions. But again, if I hadn't guessed correctly, one of those numbers, or possibly both of them, would have been negative, and all that would have meant is that the current was flowing in the other direction. That's all it means. The last calculation is the simplest of all. Go back to equation 1. Current A is equal to current B plus current C, which, and you can do this either way now, of course. I can either use fractions, 9/52 plus a 37/52, which would be 46 over 52, or you can do this as 0.17 amps plus 0.71 amps. Either way, you get 0.88 amps. And that, everybody, is how to solve one of these circuits. So now, again, several things that we found out in doing this particular case. First off, you must start with the physics concepts of conservation of charge and conservation of energy, which in practice are Kirchhoff's rules for the current junction rule and the voltage rule for a loop. You have to use those particular rules. It doesn't help to talk directly about series or parallel resistors so much anymore, because you've got a weird mix of that. Now again, there are places where you can have shortcuts to do this a little bit more quickly, but I am emphasizing the physics approach, specifically emphasizing the reasons why these look the way they look. Okay, so we would not tend to go any more complicated than this in these kinds of courses that we're teaching here, but this gives you a fair idea of what is possible. All right, thank you everybody for your attention. These videos are funded by the University of Mississippi and University of Southern Mississippi. We have technical assistance from Sydney Gouchow and Sophia Turner. Again, I'm your host, Dr. Christopher Sorolla. Thanks everybody, and clear skies.